You think you know why ice floats. Ice is less dense than water. Less dense things floats. Simple. You learned this in elementary school. Ice floats because it's lighter than water. End of story. But here's a question. Why is ice less dense than water? You'll probably say, because it's frozen. Frozen things are less dense. Wrong. That's not an answer. That's just rephrasing the question. And it's not even true. Freeze almost anything else and it gets denser, not less dense. Freeze liquid iron, it sinks. Freeze liquid wax, it sinks. Freeze liquid alcohol, it sinks. Freeze molten rock, it sinks. Everything contracts when it freezes. Everything becomes denser, except water. Water expands when it freezes. It's one of only a handful of substances that does this. And it's not a small effect. Ice is about 9% less dense than liquid water. That's huge. That's why ice cubes float, with about 90% submerged and 10% sticking out. That's why icebergs float. That's why the Titanic sank. That 10% difference is enough to tear holes and steal hells. So let me ask again, why does water expand when it freezes? What's the mechanism? What's physically different about ice that makes it take up more space than the same mass of liquid water? You can't answer that, can you? You thought it was simple. Ice floats because it's lighter, but you don't know why it's lighter. You don't know what happens at the molecular level that causes this bizarre expansion. You just accept it because you've seen it your whole life. Let me make this worse. This expansion, this one weird property of water, is the reason you're alive. If ice didn't float, if water behaved like every other substance, life on Earth would probably not exist. The oceans would have frozen solid billions of years ago. The planet would be a frozen wasteland. Every time you drop an ice cube in a drink and watch it float, you're witnessing the molecular phenomenon that makes life possible, and you have no idea why it happens. Let's start with what you think happens when water freezes. You think the molecules slow down. They lose kinetic energy. They stop moving around so much. They lock into a rigid structure. That's freezing. That's what cold does. It slows things down. Fine. But here's a thought experiment. Take a box, pack it full of marbles, shake the box. The marbles bounce around, moving randomly. Now stop shaking. The marbles settle. They pack together. They occupy less space when they're settled than when they're bouncing around, right? When things slow down, when they stop moving, they get closer together. They pack tighter. That's what happens with almost every substance. The molecules are bouncing around in the liquid state, occupying space. When you freeze them, they slow down. They settle. They pack tighter. The solid is denser than the liquid. That's normal. That's what your intuition expects. But water does the opposite. When water freezes, it expands. The molecules occupy more space in the solid than they did in the liquid. That's backwards. That violates the marble analogy. So what's going on? The answer is in the shape. Not the shape of the water molecules themselves, but the shape of the structure they form. And that shape is determined by something you've probably heard of but don't actually understand. Hydrogen bonds. A water molecule is H2O. Two hydrogen atoms bonded to one oxygen atom. The oxygen sits in the middle. The hydrogens stick out at an angle, about 104.5 degrees apart. The molecule looks like a bent stick, or a boomerang, or Mickey Mouse's head if you want to be whimsical. Oxygen is the face. Hydrogens are the ears. Now here's the key. Oxygen is electronegative. It pulls electrons toward itself. When hydrogen and oxygen bond, the electrons spend more time near the oxygen than near the hydrogen. This creates a charge imbalance. The oxygen side becomes slightly negative. The hydrogen side becomes slightly positive. Not much. The molecule is still neutral overall, but there's a dipole, a separation of charge within the molecule. This matters because opposite charges attract. The slightly positive hydrogen of one water molecule is attracted to the slightly negative oxygen of another water molecule. This attraction is called a hydrogen bond. It's not as strong as the covalent bond holding H2O together, but it's strong enough to influence how water molecules arrange themselves. In liquid water, molecules are constantly moving. They form hydrogen bonds with their neighbors, break those bonds, move around, form new bonds with different neighbors. The structure is chaotic, constantly changing. At any given instant, each molecule is bonded to maybe 3 or 4 neighbors, but those neighbors keep changing. The liquid flows because the bonds keep breaking and reforming. Now cool it down. The molecules move slower. They have less kinetic energy to break the hydrogen bonds. At some point, the temperature drops enough that the molecules can't escape the bonds anymore. They lock into position. They form a crystal. That's ice. But here's where it gets interesting. The crystal structure of ice is not random. It's not the molecules packing as tightly as possible. The hydrogen bonds have preferred angles. They want to point in specific directions. And when billions of molecules all try to form hydrogen bonds at their preferred angles simultaneously, they create a very specific geometric pattern. In ice, each oxygen atom bonds to 4 hydrogen atoms from neighboring molecules. 2 bonds from its own hydrogens pointing outward to neighboring oxygens. 2 bonds from neighboring hydrogens pointing inward to its own oxygen. 4 bonds total, arranged tetrahedrally, pointing toward the corners of a pyramid. This tetrahedral arrangement is the lowest energy configuration. It's the most stable, but it's not the most compact. The 4 bonds pointing outward force the molecules apart. They create space, gaps, empty regions in the crystal where no molecules sit. If you could shrink down and look at the structure of ice at the molecular level, you'd see a beautiful lattice, a repeating pattern of hexagons, the molecules arranged in rings with empty space in the middle of each ring. It looks like chicken wire or honeycomb. Lots of structure, lots of empty space. Compare that to liquid water. In the liquid, molecules are close together. They're not arranged in a perfect lattice. They're jumbled. Sometimes 2 molecules get very close, closer than they could be in the ice structure. There are no large empty gaps. The molecules fill space more efficiently. So when you freeze water, you force the molecules into this open hexagonal structure. You create empty space. The same number of molecules now occupies more volume. Density goes down. Ice floats. This is geometric necessity. The hydrogen bonds want specific angles. The structure that satisfies those angles has empty space built into it. You can't pack water molecules into the ice structure without creating gaps. The shape of the bonds determines the shape of the crystal. The shape of the crystal determines the density. Now let's go deeper. Let's ask why hydrogen bonds have preferred angles. Why 104.5 degrees? Why tetrahedral? Why can't the molecules just pack together in whatever configuration is most compact? The answer is quantum mechanics. Electrons are not little balls orbiting the nucleus. Their probability, the cloud shape, is determined by the quantum wave function. For oxygen in water, the electrons occupy what are called sp² hybrid orbitals. 4 orbitals pointing toward the corners of a tetrahedron. When oxygen forms bonds, it uses those orbitals. The bonds point where the orbitals point. Tetrahedral. This isn't negotiable. This isn't a preference or a tendency. This is the geometry quantum mechanics dictates. The Schrödinger equation, solved for the oxygen atom in water, gives you specific orbital shapes. Those shapes determine bond angles. Those angles determine crystal structure. Crystal structure determines density. You can trace the chain. Quantum mechanics, 12 electron orbitals, bond angles, crystal geometry, empty space in the lattice, traveling, freeing, on freezing, ice floats. Every step is mechanical. Every step follows from the previous step. There's no magic. There's no mysterious force making ice float. It's geometry. It's quantum mechanics expressed through molecular structure. But wait, there's more. Let me show you just how precisely this matters. Let's talk about what would happen if ice didn't float. Imagine you're a lake. Winter comes. The air temperature drops below freezing. The surface water cools. Normally, cold water is denser than warm water, so the cold water sinks. It's replaced by warmer water from below. This convection mixes the lake. The entire lake cools gradually. But when water reaches 4 degrees Celsius, something strange happens. Water is at its maximum density at 4 degrees. Below that temperature, it actually becomes less dense. So when the surface water cools below 4 degrees, it stops sinking. It stays at the surface. It cools further. Eventually, it reaches 0 degrees and freezes. The ice forms at the surface. It floats. It creates an insulating layer. The water below stays liquid. The ice layer protects it from the cold air above. The lake freezes from the top down, and typically only the top few feet freeze. The bottom stays liquid. Fish can survive. Aquatic life continues. Now imagine ice didn't float. Imagine ice was denser than water, like almost every other solid. Winter comes. Surface water cools. It freezes. The ice sinks. More surface water is exposed. It cools. It freezes. That ice sinks too. Layer after layer of ice accumulates at the bottom. Insulated from the summer sun by the liquid water above, it never melts. Season after season, year after year, ice accumulates. The lake gets shallower. Eventually it's solid ice with maybe a thin layer of liquid on top in summer. But that liquid refreezes in winter. More ice sinks. After enough cycles, the entire lake is solid ice year-round. The same thing happens in the oceans. Ice forms, sinks, accumulates on the seafloor. The oceans freeze from the bottom up. Once the ice is at the bottom, sunlight can't reach it. It can't melt. It's locked there. The oceans gradually turn into solid ice. This isn't speculation. We can model this. If ice were denser than water by even a few percent, Earth's oceans would freeze solid within a few million years. The planet would enter a permanent snowball state, frozen, lifeless. But ice floats, so lakes freeze on top. The ice insulates the liquid below. Aquatic ecosystems survive the winter. The ice melts in summer. The cycle continues. Life persists. And why does ice float? Because water molecules are bent at 104.5 degrees. Because oxygen has sp spread hybrid orbitals. Because the tetrahedral arrangement of hydrogen bonds creates hexagonal lattices with empty space. Because quantum mechanics dictates electron orbital shapes. One bond angle. That's the difference between a living planet and a frozen rock. Let me show you the evidence. Let's prove this is real. Take a plastic bottle, fill it with water, seal it, put it in the freezer. Come back in a few hours. The bottle is deformed, bulging, sometimes cracked. The water expanded with enough force to deform or break the plastic. You've witnessed molecules rearranging into a structure with empty space, generating enormous pressure in a confined container. Or do this. Fill a glass with water, mark the level, add ice cubes. The level rises because the ice displaces water. Now wait for the ice to melt. Check the level again. It's back where it started. The melted ice occupies the same volume as the water it displaced. This proves the ice was less dense. Less mass per unit volume means it floats with only parts submerged, and when it melts, the volume change exactly compensates. Or look at ice under a microscope. Freeze a thin layer of water on a slide. Look at the crystal structure. You'll see hexagons, six-sided patterns. That's the hexagonal lattice. That's the empty space. That's the geometric arrangement of hydrogen bonds forcing molecules apart. Or measure the density. Weigh a known volume of water. Weigh the same mass of ice. Calculate the volume. Ice occupies about 9% more volume, 1.09 times bigger. Density is mass divided by volume. Same mass, bigger volume, lower density. Ice floats. We've measured this thousands of ways. We understand it completely. We can calculate the density of ice from first principles. Start with the mass of a water molecule, 18 atomic mass units. Calculate how many molecules fit in the hexagonal crystal structure. Calculate the volume of the unit cell, the repeating structure. Divide mass by volume. You get 0.92 grams per cubic centimeter. Liquid water is 100 grams per cubic centimeter. Ice is less dense. It floats. And we've tested this with other substances. Heavy water, D2O, where the hydrogen is replaced with deuterium, a heavier isotope. Heavy ice also floats on heavy water. Same structure, same expansion, same hydrogen bonding. Or water with dissolved salts. Salt water has a slightly different freezing point, but ice still floats. The fundamental mechanism is the same. But let's push to the limit. Let's ask why quantum mechanics gives oxygen spread orbitals. Why that geometry? Why does the Schrödinger equation produce tetrahedral orbitals for oxygen? The answer is math. The Schrödinger equation is a partial differential equation. When you solve it for an electron in an oxygen atom, you get wave functions. Those wave functions have specific shapes. The shapes minimize the energy while satisfying the constraints of quantum mechanics. The sp-sprad hybrid orbitals emerge from the math. They're not designed. They're not chosen. They're the solution to the equation. But why is the Schrödinger equation correct? Why do electrons obey quantum mechanics? Why does nature work this way? We don't know. Or rather, we can describe it, but we can't explain it in terms of something simpler. Quantum mechanics is fundamental. It's one of the two great theories of modern physics, along with relativity. We've tested it exhaustively. Every prediction matches experiment, but we can't derive it from deeper principles. The equations are what they are because that's what matches reality. So when you ask why ice floats, the chain of explanation goes like this. Ice floats because it's less dense than water. It's less dense because the crystal structure has empty space. The structure has empty space because hydrogen bonds arrange tetrahedrally. They arrange tetrahedrally because oxygen has sp squared orbitals. Oxygen has sp squared orbitals because that's the solution to the Schrödinger equation. The Schrödinger equation is correct because it matches what we measure. That's as far as you can go. Eventually you hit bedrock. Fundamental laws. They don't reduce further. They just are. But look at what we've connected. We've linked ice cubes floating in your drink to the quantum mechanical structure of electron orbitals. We've shown how molecular geometry determines planetary habitability. We've demonstrated that one bond angle, one geometric constraint from quantum mechanics is the reason lakes don't freeze solid, the reason aquatic life survives winter, the reason Earth didn't turn into a snowball billions of years ago. And this isn't speculation. This isn't philosophical musing. This is measured fact. We can calculate the density of ice from quantum mechanics. We can predict the structure from bond angles. We can measure the expansion. We can test every step of the chain, and it all matches exactly. So the next time you see ice floating, the next time you drop a cube in water and watch it bob at the surface, remember what you're seeing. You're seeing quantum mechanical electron orbitals expressed through molecular geometry. You're seeing tetrahedral hydrogen bonds forcing molecules into a hexagonal lattice with empty space. You're seeing the reason life on Earth exists. Ice doesn't float because it's lighter. Ice is lighter because quantum mechanics dictates orbital shapes which determine bond angles, which force geometric structures with empty space. The floating is a consequence. The cause is buried 5 levels deep in the structure of atoms and the mathematics of wave functions. You thought it was simple. Things that are less dense float, but you didn't know why ice is less dense. You didn't know about hydrogen bonds. You didn't know about tetrahedral geometry. You didn't know about quantum orbitals. You didn't know that this one property, this expansion on freezing, is the thread connecting atomic physics to planetary habitability. Everything connects. The quantum mechanics of electrons determines the chemistry of bonds. The chemistry of bonds determines the structure of crystals. The structure of crystals determines the density of ice. The density of ice determines whether it floats. Whether it floats determines whether oceans freeze. Whether oceans freeze determines whether life survives. One chain, unbroken, from the Schrödinger equation to the existence of fish, from electron orbitals to planetary climate. That's not mysterious. That's magnificent.